Okay, back to this example. So let's read through it first. We've got a river flowing toward a lake, I like this, at an average velocity of 3 meters per second, at a rate of 500 meters cubed per second, at a location 90 meters above the lake surface. Okay, a lot going on here. Determine the total mechanical energy of the river. Okay, total mechanical energy per unit mass, I like that. And the power generation potential of the entire river at that location. Okay, power generation potential. Okay, so lots of little details here. So let's get to it. Now, first thing I want to mention to you is that meters cubed per second, this right here, this is a volume flow rate, okay? That's connected to our mass flow rate by saying that our mass flow rate is equal to our volume flow rate times density. And luckily, because this is water, we can find out density pretty easily just by looking up online or in your textbook. That's a good place to look too. Okay, so here's a nice little picture of it. So we've got river water flowing, and we also have this height difference. Now, hopefully, based on our talks of energy, you're already realizing that this means I'm going to have kinetic energy here, and I'm going to have potential energy due to the height difference. So I actually have both of those. Both of those are a way I can get energy out of the system. So what kind of energy is available? Both. Okay, so how do we go from there? Well, it might be good to write out our total energy equation. Now in this case, I didn't add on the U term. I could have, but it doesn't mention any sort of temperature difference or that this temperature is greater than atmospheric for some reason. Like the river is going to be the same temperature as everything else. If there's no temperature difference, I won't have any issues or I won't have any changes due to internal energy. So I'll probably leave it off. Now this right here is my total energy per unit mass. Wait a second, what's mechanical energy of the river water per unit mass? If I can solve this, I already have one part done. So one thing you might notice is there's no mass in here. I don't need it because I'm dividing by the mass. So I have a velocity. Okay, check. I've got a height difference. Gravity, what are you going to be? Well, it's 9.81. If your teacher says 9.8, they're welcome to do that. But for me, please, 9.81 at least. That is more accurate. Okay, so I plug it in here. This right here is my potential energy. I should do a lowercase. Let's keep the, there you go. And this right here is my kinetic energy. It's really hard to draw lowercase for both of those. And this is that helpful conversion once again. 1,000 meters squared per second squared is 1 kilojoule per kilogram. You need to do that because none of these guys actually have kilojoules or kilograms in them. They have meters squared per second squared, so you're going to have to convert there. And I'll get that I have 0.887 kilojoules per kilogram of energy, mechanical energy in the river water per unit mass. Nice. Okay, now if I want to find the max power generation, I'm saying I managed to get every little bit of this kinetic energy and potential energy out of it. Incredible, well done there. Well, that's going to be equal to my energy per unit mass times my mass flow rate. Now we weren't given a mass flow rate, but I've already kind of clued you into how we're going to get that. Because our mass flow rate is equal to our volume flow rate times the density. So I did that. You're like, wait a second, where did the density come from? Well, this is one I would definitely strongly suggest you memorize. 1,000 kilograms per meter cubed is the density of water. Technically, it's 997, but 1,000 is so much nicer. It used to be 1,000, then we realized we weren't being accurate enough and they had to fix it. That's just how life is. And so we get 500 kilograms per second of water as our mass flow rate. Okay, if we have that, we can then plug it back into our original equation. And so we have our mass flow rate here times the energy per unit mass, and we get 443,500 kilowatts. That is a lot of energy, which probably explains why we make dams to use that energy to do something useful, to create electricity, to power homes. Now, when we're powering homes, though, not all of this gets to electricity, okay? Maybe 50% of it, 20% of it does. But in the end, I'm not having to work to produce this energy. Nature's just doing it automatically. So I don't mind if I only get even 10% of this. I should have written that as percent. There we go. We'll get rid of the dot. Gets there because I'm still producing electricity for nothing. So long as I'm making enough money to actually keep my dam running and paying the people who work there and all the things that are necessary, it is worthwhile. Okay, so that's the end of this example. Thank you so very much. Hopefully you learned something, and I'll see you all next time. Have a great day.